Good evening. My name is Sabrina Sartori. I'm a professor at the University of Oslo. I'd like to welcome Martin Green. He is the leader of Materials for Energy and Sustainable Development Group at the National Institute of Standard and Technology. Thank you for joining us.
My pleasure.
Professor Green, what is the role of material science in technology?
Well, materials are technology enablers. So the way I explain it to anybody who's not in the field is that materials are so important to human development that we have named entire periods of history about the name of the most advanced material we had. So we had the Stone Age, we had the Bronze Age, the Iron Age, and now we could think of ourselves as being in the Silicon Age because silicon has enabled the information revolution and all of the electronic devices and computation that we take advantage of now. So it's extremely important. It's a driver. Many technologies are limited by materials developments. Once the development is there, there's a critical application for it and a new technology takes off.
What are your thoughts on the emerging field of material informatics? How can it accelerate materials design and development?
Right. So materials informatics I consider to be one part of a much larger program which is now going on in the United States and spreading to other countries called the Materials Genome Initiative, known as the MGI in the United States. And it consists basically of, well, the goal of the MGI is to reduce the time from invention and commercialization of a new material by half, and also to do it at significantly lower cost. The way that's going to happen is through a lot of computation and modeling, simulation and modeling, because simulation and modeling has become 100 to 1,000 times more powerful over the last 10 years. And so now we can simulate materials properties and phase equilibria in ways that we could not do it just 10 or 15 years ago. And so you can use modeling and simulation to replace some amount of experimentation, which is much more costly and much more time consuming. And so we hope that we can, well, the MGI is going to change the way material science is done in the next 10 to 20 years. We'll be doing materials discovery and commercialization in a very different way than we do it today. Informatics will be part of that because we're going to be creating enormous amounts of data, either model data for computer or simulation data, and also experimental data using high-throughput material science methods, otherwise known as combinatorial material science. But we're going to be creating entire bodies of information that will require data mining, and the data mining is done through informatics algorithms to find relationships that are not evident to the human eye. And in fact, you may do an experiment for one purpose. That data will be archived someplace. Somebody else may come in 5 years later and say, I'm interested in that material system. And they may mine the data for something completely different that you never even thought of, that the original creators of that data set never thought of. And that data can constantly be mined for new relationships.
Let's talk a little bit about your research. At NIST, you are focusing on developing MEMS-based nanocalorimeters to detect and measure thermal behavior of materials with nanojoule sensitivity. How does your approach differ from that of current devices?
Yeah, let me just first say that NIST is a metrology laboratory. So when we study materials, the thing that we're most studying is some new way of measuring the property of a material, an interesting property of a material, either more accurately or measuring some property that would have been difficult to measure before. The field of calorimetry is large, but the field of nanocalorimetry, and now we even are making picocalorimeter devices, is very small. It's a small club. There's maybe a dozen people around the world who are, doing research in this area. What we are doing, and so the advantage is that we can look at the kinetics and thermodynamic properties of very small amounts of material, which is appropriate because so many materials today are nanomaterials. And if you took, now you can take all the nanomaterials, you can take a large amount of it and put it in a regular calorimeter, but then you're going to see some average property of millions and billions of nanoparticles. But if you want to look at the specific properties of just a few of them, you have to have a very, very small sample. And that means you have to have an extremely sensitive device. And so we've been making devices that are more sensitive than anything that's been made before. The lead person on this is a person named David Levan, who has done this work for about 10 years now. And so he's looking, for example, at such subtle chemical reactions as the binding of a drug molecule on a cell wall. And so if we know that binding energy, we can say something about the potential effectiveness of the drug. Or if you have two extremely thin films, nanometer thickness films, that are reacting together to form another reaction product, we can measure that, even though it's a very small amount of mass. And nobody can do that now. The other thing that we do in the design of the nanocalorimeter is we have the mass of the nanocalorimeter device extremely small. So that enables us to heat it and cool it very rapidly. And so when you can do that, you can look at kinetic regimes that are much, much faster than anything that could be looked at in a bulk material. Mm-hmm. So we're really opening up new metastable observations that wouldn't be seen in a bulk material.
Thank you. Very interesting field. We have been talking with Professor Marty Green from Sabrina Sartori. Thank you for watching.
Thank you.